Okay, so this is Force and Motion at Home lesson for Monday, 11/16. So in this lesson, I'm gonna go through a few things on the slide, and then there is going to be an article that we are gonna listen to and answer some questions. So thanks to you, we understand that even though the thruster force is the same strength on all pods, this pod was affected differently because it is more massive. The thrusters could only slow the pod, and since it didn't stop it, it hit the space station. Our team is thinking about a rescue mission, but we also learned that the crash made the space station move. We know the collision caused the pod to move in the opposite direction, but is the pod faster, the same speed, or slower than the space station? How far away from the space station is the pod? How fast is the pod moving? Is a rescue mission possible? Once again, we need your help with our questions. So we have already learned that it was actually claim 2 that was true. So the thrusters only slowed the pod. It didn't stop the pod. It hit the space station, which made it bounce and move in the opposite direction. Claim 2 was supported by the evidence. Since the pod was more massive than usual, the usual thruster force only slowed the pod rather than stopping it. So that's what we learned about mass. The more mass, the harder it is to stop it. So the pod had to have more mass because it was carrying those extra rocks. It was hard. The thrusters weren't enough force to stop the pod. So now we're in chapter 3, and we have a new word, and that word is collision. And that's what we're going to read an article about today. And a collision is the moment when two objects hit each other. So here is pool table balls. So here's the cue ball and a solid ball. So when they hit, what's going to happen? And that's what we're going to really investigate today. So our question that we're working off of is, after the collision, how does the pod's motion compare to the motion of the space station? So we have some claims, and this is what we're going to think about as we read the article. After the collision, how does the pod's motion compare to the motion of the space station? Claim 1, the pod is moving faster than the space station. Claim 2, the pod and the space station are moving at the same speed. Claim 3, the pod is moving more slowly than the space station. Okay, so we are going to listen to the article, but you can also follow along in your book. In the back of the book, under C1 is the article, and it is also linked here in Amplify. So just like the last time, I'm going to let Amplify read it to us.
Crash. Forces in collisions. Say you're in a car driving down the highway at 60 miles per hour, and splat, your car hits a bug. It probably seems like all the force of that collision acted on the bug. After all, the bug is splattered across your windshield, but you in the car probably didn't feel a change. However, not all collisions result in such different results. When two bugs that are about the same size fly into each other, the effect on both bugs is similar. They're both bumped off course by about the same amount. How can some collisions affect objects the same way, like the two bugs, and other collisions have vastly different effects, like the bug splattered on the car windshield? The world is full of things running into each other, and what happens as a result of those collisions depends on the physics of force, mass, and velocity. Below, you'll read about everyday examples of how collisions affect objects around us. How to stop a pool ball. In a game of pool, also known as billiards, you hit a white cue ball with a long stick called a cue. You want the cue ball to knock other balls, sitting stationary on the pool table, into the pockets on the edges of the table. However, you don't want the cue ball to follow them into the pockets. Hitting the cue ball can be risky. Whether they know it or not, pool players use physics to their advantage. If they set up the collision just right, the cue ball comes to a complete stop after the collision, while the colored ball starts moving. How does that work? During a collision, both balls experience the same force, but in opposite directions. When a moving object collides in a straight line with an object of the same mass that's sitting still, both objects experience the same amount of force. However, the motion of the balls changes in different ways because of their initial velocity and the direction of the force on them. The moving object changes its velocity by going from motion to rest, while the still object goes from rest to motion with the same velocity the moving object used to have. Since the force is experienced by both balls, but in different directions, the colored ball moves across the table while the cue ball stops. That gives you the chance to win the game. Bump. If you've ever driven a bumper car at a carnival or fair, you've already studied your fair share of collisions. After all, bumping into other cars is the whole point of bumper cars. It's right there in the name. If you and your bumper car bump into a car carrying a friend who's about the same size as you are, you might expect that both of you would experience equal forces. You have about the same amount of mass and are about the same size, so if you're both already moving, you bounce away from each other to about the same distance. But what if you bump into somebody with a different mass? Say you bump into your little brother, who has less mass than you do. You bounce back just a little bit, but your brother and his bumper car go zooming across the floor. Would you believe that the forces you experience during the collision are still exactly the same? They are. Your brother moved far away from you because he has less mass than you do. The amount of force you both experience was enough to send him flying at a high speed. You didn't travel as far as he did because you have more mass. The effect of that same amount of force was only enough to change the velocity of your mass a small amount. The distribution of forces in a collision between your car and a bug isn't so different from the forces in a collision between your bumper car and your brother's. In both collisions, both objects, or people, experience equal forces. It's the difference in the masses of the objects, or people, that makes the effect of the collisions dramatically different. Since the bug is so tiny, the effect of the collision with the windshield is large enough to suddenly change its velocity by a lot. So much that it ends up exploding on the windshield. Nothing so terrible happens to your brother in the bumper car when you run into him, though. Your mass and his mass aren't very different, so the effects of the equal forces your collision produces affect you only slightly differently.
Okay, so we have a Flipgrid question now that you should be answering this in the link. There's a link in Google Classroom to this Flipgrid. Explain why the two bumper cars end up going at different speeds after the crash. So this is a picture from that article that we just read about. We have this guy with a mass of 70, this little guy with a mass of 32. They hit each other, they go in different directions, but this little guy is going faster. Why does that happen? So you're answering that in the Flipgrid.